Okay, let me put this here. Perfect. So welcome everybody. This is 4th DGD session, and as requested, all of you, in this session I'll be reviewing your midterm syllabus. Not fully. I'll be covering chapter 22, 23, and 24, and not 25 because I covered that in my recent DGT session, that is 3rd DGT session. So here's gonna go. I'm gonna repeat again. What I'm gonna do today is I'm gonna go concept by concept every chapter. Then the previous questions, what I did for you in the 1st, 2nd, and 3rd DGT, and then some new questions as well, just to give you the practice. And I hope that'll be enough for your revision. I'm waiting for the comment. Yes, I'll be uploading these notes as well. Everything is going on YouTube and Brightspace. Okay, so let's start with electric fields. As you know, electric field at any point where electric charge Q0 is present is given by, let me put my marker as well, is given by E as Fe by Q0. The point to note here is that electric field is a vector. That means it is in the same direction as force. Then there is another Coulomb's law which states that electric force between 2 point charges Q1 and Q2 is given as Ke Q1 Q2 by R square. Again, force is a vector, so you have to take care of the direction as well. Where Ke is 9 into 10 to the power minus into 10 to the power positive 9 Newton meter square per Coulomb square. That is the constant right here. You have to remember this value. Your prof won't give it to you. He might, but a lot of prof doesn't give. So, and if the charges are discrete, then electric field due to collection of point charges is given as E as Ke Q by Ri square. I is the coordinate of the point charge. So it's point charge number 1, point charge number 2, point charge number 3. So then there will be a summation sign as shown because of the collection of point charges. Perfect. Let's go to the questions that we solved in DGT1. Not all of them, some of them that are covering the concept. So the first question, so we solved about the electric force between 2 sodium and chlorine ion separated by some distance. This is the direct application of Coulomb's law. I'm not solving this because I solved this in previous DGT, so I'm just giving you the concept here, that how I solved. Okay, so it's direct application of Coulomb's law, and the formula you apply here is Ke Q1 Q2 by R square. Question B says, answer, change if the sodium ion were replaced by lithium ion. No, it doesn't matter the type of ion, it depends on the distance between them and the charge. Moving on to the next question. We solved about 2 small beads, Q1 and Q2 are fixed in the horizontal insulating rod of length L, length T. The bead with charge Q1 is at the origin as shown in the figure, and then another bead Q2 is at distance D from Q1. Then at what position X is third bead in equilibrium. So the point to emphasize here is that the charges are in equilibrium only when the total electric force on the charge is 0. The point of equilibrium is when the total electric force or force on that body is 0. That is the point of equilibrium. This is what you have. So you write the equation for the force and you equate it to 0. That's where you will find where the third small charge is located. Again, if you want to see exact solutions, you go back to the previous DGT sessions. You have the notes, you have the video. I'm giving you the concepts here for the previous questions. Moving on to the third question. And I'll be going little fast today because I have a lot to cover. So hope you guys don't mind this. Moving on to the third question. Here we have a question, a parallelogram in which charges are given at two corners, Q, that is corner A and corner B. I'll name them as A and B. Then, thank you, Anthony. Then at point A and at point B, then we have to find the electric field at point B. Point B is here. Again, the concept here to remember is electric field is a vector. Okay, that means you have to consider magnitude and direction. That means due to point A, it's straightforward because it's on the horizontal axis. That means the direction is in I cap. But due to point B, it is in the direction minus I cap plus J cap by root 2. How I got this, I solved that in the DGD, but I'm saying when I write magnitude plus direction, there will be magnitude as well. So that's how I get electric field at point B. Okay. Again, the concept is that electric field is a vector. A lot of students, when I was in undergrad, I used to do this mistake as well, that I used to write only magnitude and leave the answer there. You have to consider direction. Okay. Moving on to the fourth question. Consider n equally positively charged particles, each of magnitude q. So if you remember, we had the question in which we had the ring and we had all the charges distributed uniformly and discrete charges across the ring. Then we had to find the electric field at the point along the horizontal axis at a distance x, axially symmetric. So due to the axial symmetry, the vertical component of electric field at point P cancels out. We have only horizontal component, and that's how we get it. So here concept is we check for the symmetry. That's what you have to think in the exam, that if somebody asks you here, you say it, the thought should come in your mind that yes, because the charges are placed symmetrically around the point where I have to find my electric field, then my vertical components cancel out, or only horizontal remains due to this and this. Due to this and this. Let's go to the fresh questions. These are the questions I chose today. They are not very easy, not very difficult, and I chose the mediocre ones. Okay, just to brush up your concept. So a point charge plus 2q is at the origin, and there's another point charge minus q that is located at distance x, as you can see on your screens. Find a symbolic expression for the net force on the third point charge q. This is the point charge. We have to find the electric force at this point charge, that is at distance d from plus 2q and at some distance from minus q. So force due to positive charge 2q, that is this, is given as ke 2q square by d square. This is again ke q1 q2 by r square. And for force due to negative charge, this one is given as, I'm gonna write it. If you guys have problem, you can ask me. Okay. Okay. Somebody has problem with that? If you all agree, then I'll move on. Just type yes. So there was a negative sign outside. I took it inside, so it was supposed to be minus I cap plus j cap. So I changed it to plus I cap and minus j cap. Perfect. Yeah. And the total force is, again, you add them vectorially, F1 plus F2. So you add this and this. That's your total force. Moving on to the second question. We have 3-point charges. Now, again, this is the question where I was emphasizing on the symmetry. You'll see. So these are on the circular arc, 3-point charges. One is negative 2 nanocoulomb and two are positive 3 nanocoulombs. They're located right here, and right here. They are located on the circular arc. That means there is a symmetry in the problem. Now we have to find the electric field at point P. Again, say yes if the vertical component of the electric field at point P vanishes. Perfect, you guys. Getting hang of it, right? So because it goes like this, at here it goes like this, then only horizontal component remains. And vertical cancels out. So due to symmetry, net E field component, net E field component, not E field, wait, Y component of E field. Y comp of E field is 0. And then Ex can be written as E due to 2-point charges, X component of that, or E total minus E due to negative point charge. Now that I can write as Ke Q by whatever the radius is given, r squared, where Q is plus 3 coulombs and Q is 2 nanocoulombs. Everybody gets this? If you are okay, I'll move on. Perfect. So this is exactly what I wrote here is same as this. I wrote it before. I didn't realize that I wrote it there. So electric field at point P is the total X component due to 2-point charges and subtracting the negative point charge electric field. Now the B part of the question is, just a sec, let me clear. And for Q also, just to mention, I'm not writing a negative sign here, because I've already considered in the equation negative sign. Okay. Now find the electric field that would be exerted on a minus 5 nanocoulomb charge if at point P we have minus 5 nanocoulomb charge I forgot I cap. Then force is given as QE. You did find E total in the A part of this question, so just put that and you have substitute Q as -5. You'll get total force. That's okay. Moving on to the third question. So 3 positive charges are given, and these are equal positive charges are placed at the corners of or the edges of an equilateral triangle. That means all the sides are of same length and the angle they subtend between each other is 60 degrees. That's the meaning of equilateral triangle. Assume 3 charges together create an electric field. They will, for sure. Sketch the electric field lines in the plane of the charge. So I'm gonna sketch it for you. So you will have electric field lines like that. So I'm just sketching roughly, okay? Yeah, let me. Okay. Now, based on what I have drawn in part A, answer part B for me. Find the location of point where the electric field is 0. Anybody, any guesses? Where the electric field is 0? Okay, Billy says in the middle. What about the others? Yeah, perfect. The answer is center. So at the center point, there is no electric field exactly at the center, and there are electric field lines, but they cancel each other. That's why I have not drawn them. That's why I've drawn them like this, portraying out from the center triangle. Okay, I think that addresses your question, Bill. Perfect. Okay, I'm waiting for your comment. Okay, perfect. Let's go. So at the center, you can prove this mathematically as well, or you can say by symmetry. At the center, E field is 0. Excellent. Let's go. What are the magnitude and the direction of electric field at point P? Okay. At point P, any guesses for the direction of electric field? So at point P, what is the direction of electric field due to these 2 point charges? This one and this one. What is up? There is no up. Either J cap or I cap. Vertical or horizontal. That is J cap. Perfect. Thank you, Billy. So, as you know, you can write that simply. I'll write it. Electric field. So again, due to what the hell? Yeah, due to symmetry, horizontal component cancels out, and only vertical component is left. Component adds up E total Right, point P is given as E1 j cap plus E2 j cap. That is y component. Let me write it y. E1 y, E2 y, not j cap. That is a little confusing. When you write due to these things is actually it will be simply, let me write it, KEQ by A square to somebody's mic is open. If you are not asking any question, can you please turn off the mic? Okay, wait, let me turn off for you. Are you guys getting my voice? You're getting my voice, right? Okay, perfect. Okay, please don't open the mic if you're not asking questions, because that creates disturbance for all of us. Okay. Sorry for the break. Let's go on. So this is the answer. Everybody agrees with that? If yes, I'll move on to chapter 23. Okay, I'll move on. Chapter 23 is about continuous charge distributions in Gauss law, and it briefly I'll sum up the points. The main points are as follows: electric flux through any closed surface is directly proportional. This is the symbol for directly proportional to the number of electric field lines penetrating. What is the denominator under KEQ by cont? It's just a square. Wait, I was just reading. This is a square. The distance. A is the distance given in the figure. Okay, back to chapter 23. Electric flux through any closed surface. So that point is the closed surface. Emphasize on that. Closed surface is directly proportional to the number of electric field lines penetrating the surface. So flux through any closed surface is given by the surface integral E dot dA. So flux is a scalar quantity, is not vector quantity. That means it has no directions. Perfect. That means it's a number. A Gauss law says that net electric flux or net electric flux through any Gaussian surface, electric flux. No, I'll tell you, believe what's the meaning of this little thing here is that means it's a closed surface. This circle means for a closed surface. So in integrals, whenever you say that, that means, yeah, it's okay. So whenever you write that for any surface integrals, let's say v dot dA or anything, And if you type it like that for any surface integral, that means this is not a closed surface. For any closed surface, you draw this. That means it's a closed surface. Or you write this surface. That means it's a closed surface. Okay. I mean, in research, it matters. And also, when you want to be perfect, then this is a point to emphasize. Okay. And Gauss law is not applicable outside the realm of closed surfaces as well. That's why it's important to put it here. So net electric flux, not field, net electric flux through any Gaussian surface, is E dot ds equals to charge enclosed, that is charge inside any Gaussian surface. Let's say this is a worst drawn sphere ever, and there is a charge q inside. Then the total electric flux is given as the charge enclosed divided by epsilon naught. Okay, and there is no point. You can draw a cube as well, and you can say this is a Gaussian surface. But again, the mathematics, due to the symmetry and due to the fact that electric field is perpendicular to every point on the spherical surface, that's why we always consider Gaussian surface as a spherical surface. But you can prove this using cube as well as a Gaussian surface, but that'll be a lot of mathematics, heavy mathematics, so you don't want to go through that. Okay, just sphere simplifies that. Now electric field due to, also in this chapter we cover electric field due to continuous charge distribution. Electric field due to continuous charge distribution is given as E, because as I told you before, any surface, if it has continuous charge distribution, well, that means you can break it in infinitesimal points, or this looks like a area element, infinitesimal area element, and you can say surface charge density related to it, sigma dA, and then you integrate over whole infinitesimal circular points to cover the whole area. That's why you do the integral when there is a continuous charge distribution. This is related to the question some of you asked me in the last EGT. I just want to brush it up. That's why you do the integral. If this is clear, I'll move on to the questions. Just type yes, or say no, or ask any question if you have any doubt. Perfect, thank you. Let's move on to the questions. Again, I'll be brushing up the questions I previously did and some new questions as well. This is the question you guys have comments about. Okay, so a uniformly charged rod of length L and total charge Q lies along the x-axis as shown, and that means it's a uniformly charged rod. That means it is a continuous charge distribution. That means you have to apply integrals. That's how you identify where you have to apply integrals. And in the question and first part, we have to find the electric field component at point P. Electric field component at point P, that means it has two components in EY cap direction and EX cap direction. You integrate over the whole length. You take, as you remember, I hope you remember, all of you, you take the infinitesimally charged element dx containing the charge dq, then you integrate over whole length, goes from 0 to L. That makes sense, right? I can move on. I assume if nobody's writing, then it's yes for all. Okay, so there are these two questions. These are the direct application of Gauss law and some symmetry consideration. I'll read them for you. So in the first question, it says there is a cube and there is a 170 microcoulomb charge that is enclosed inside the cube at the center. So what is the flux through whole surface of the cube? It's just cube enclosed divided by the epsilon naught, that is Gauss law. And would your answer to either part of A or B changes if the charge were not at the center? Yes, for the part A, where the flux through each surface will change, but total flux through the cube won't change because of Gauss law. Question number 18th or fourth question is a particle with charge plus 12 microcoulombs is placed at the center of a spherical shell of radius 22 centimeter. Doesn't matter the units. What is the electric flux through the surface of the shell? Again, it's a spherical shell, then that is Q enclosed by epsilon naught. Okay, and for the hemisphere, you divide it in half, then it's half of Q enclosed by epsilon naught. Do the result depends upon the radius? No, not at all. Flux is not dependent on the radius for the Gaussian surface. Okay, I did half by using symmetry considerations. I'll move on to the further questions. These are the fresh questions. Okay, this is again the rod one, the favorite. A thin rod of length L, instead of on the right of the axis, it's now symmetrically placed at the origin, as you can see in the figure, and there is a uniform charge per unit length lambda. That means there is an integral involved. I have to do the integral to find the total electric field. Show that the electric field at point P a distance d from the rod is has no component x, so there is no x component, and there's only y component. That is given as, you have to prove Ex as 0, Ey as 2ke lambda sine theta by d. Where theta naught is given by this angle. Okay, again, what is dEy? We all agree, right, that Ex is 0. Ex is 0 because if you take the element here and the same element here, Ex cancels out on both sides every situation, no matter where you consider in small element dx. Okay, because there's always a symmetrically placed other element on the same side, on the other side, opposite side of the origin. Okay, due to symmetry. Perfect. Now again we have to find Ey. So E total is Ey. P total can be given as somebody's typing. I'm waiting for them to type. That there is no component X because of symmetry. Yes, this is because of symmetry, because it is placed around equally around the origin, symmetrically around the origin. So the rod is minus L 0 to L by 2 and 0 to minus L by 2. That makes sense. No, if so, that's the thing in physics. No, if you give physical argument that that's why, and it's right, then nobody can cut your marks. That's the beauty of the subject. This is not mathematics, so that's the difference between maths and physics. Who agrees with me on this one? What I wrote as EDX, and there is a cos theta component. You agree with this? All of us? Or I'll write it like this. That's better, according to the question. Minus L by 2 to positive L by 2. Let me write it better. Right, then I can do this. I can take 2 instead of. I can substitute for cos theta. That will be d by x squared plus. Whoa, what's happening? Just sorry, very sorry. I think something closed my OneNote. Okay. I don't know what happened. It's weird. So I can write this as x squared plus b squared. Everybody agrees with me? Instead of 1 by 2, now I'm writing power as 3 by 2. Right? And this is the same integral that I solved in this question in DGT second. If you guys want me to solve it, I can solve it right here. If not, I'll give you a very cool trick. You don't have to do the integral at all, because of the symmetry of the problem. There is 3 by 2 because of the cos theta. Cos theta is given as d by x squared plus d squared. Yeah, I'm gonna give you the trick anyway. So that's my aim. Solve it smart and simple. Okay. So I know this is how it will be, and I'm gonna write you the final answer for you guys. Okay. I solved it before the lecture, and that it came out to be I already knew the answer. How I knew this will be the answer? Do you see what is this quantity? Oh, what is this quantity? This is sine theta naught, and it has to come sine theta naught because I'm waiting for Billy's comment. He's typing. Yeah, I can move out the constant. So this has to be sine theta naught because of the symmetry. Only vertical component remains. So only the component in the direction remains. And because this rod is symmetrically placed around the origin, that means total electric field due to a whole rod that is symmetrically placed can be written as simply as the one that is given in the question to prove as well, because as you can see this, because in the end you have only EY component, and if you see rod as a single quantity, then there has to be sine theta naught in the answer. So that's why I already knew this will be the answer before doing it. So you can directly jump from this point to this, stating that we assume x as d tan theta and dx as d sec square theta d theta, and doing the integral we get this. Because I knew the answer would be, there would be sine theta naught in the answer. Did you get how I knew beforehand? Yeah, it is given in the question as to prove as well, but I knew because this is symmetrically placed around the origin. That means I can consider it as one unit, and I know because of the symmetry there's only EY component. So at point this is, I know by my Coulomb's law, this is E cubed by R square, and R is given as D square, and K I can write it as lambda D, D to D cancel, and there should be sine theta naught component. And 2 for, because the length is 0 to L by 2 and 0 to minus L by 2. That's a compelling argument, right? That's called intuition. You know what should be the answer before doing. Okay, this is just the okay, let me tell you this. This is just the intuition. This is not the perfect way to solve it. You can't solve it in the exam like this. This is not right. Let me tell you again. This is just the intuition part of it. I knew this will be, because this is an argument. You can't write it. This is this, and my TA told me that this makes sense. Your prof would gonna give you 0 on that. Okay. Let me delete it from here so that it won't make confusion to anybody. Okay. So everybody is cool with the integral? If say yes, then I'll move on. If no, I can go ahead with the integral. It's exactly same as the last second DGD. The problem we did with the rod, instead of symmetrically placed around the origin, it was shifted from the origin right here. So I can move on. I have your permission. Okay, so that's it. Okay, what if your result to part 8 show that the field of rod of infinite length is E if the length goes to infinity. Okay, if the length here goes to infinity, this is the length, then what should be the answer? The answer should be everybody agrees with this, right? This should be your answer if L goes to infinity. I think it makes sense. You just put L equals to infinity here, approximate it, and then L to L cancels out, and D is nothing in comparison to L. So you say L by 2 whole square plus D square is approximated as L by 2 whole square, and then you cut it. They cancel out. Okay, let's go to question number, that is question number 5th of today's, no, whatever the numbers. So question number 17, it says that find the net electric field through the cube. Any guesses here? Net electric field, electric flux through the cube. What should I apply here? Just give me some guess. I think it's a good revision if you give me some guess. I'm waiting for your comment. Anybody? 3 nanocoulomb by epsilon naught, is it? That's what you want me to say? Right? That's what you meant to say, right? That 3 nanocoulomb by epsilon naught? But still thinking. Okay, go ahead. I'll drop the answer in the meanwhile. You're right. It is 3 nanocoulomb by epsilon naught. Let's call it charge instead of proton. And yes, our favorite Gauss law says that flux through any surface, any closed surface, is only dependent on the charge enclosed, that the charge inside. Doesn't matter what is the charge outside. Let's say I'll put this, thousands of charge outside. Flux doesn't change. It only depends on the what is inside. That makes sense? Perfect. Waiting for another comment. Okay. Part B. Can you use the Gauss law to find the electric field on the surface of this cube? Now this is the question. Again, your voting question comes again. So can we use the Gauss law to find the electric field, not electric flux, on the surface of the cube? Again, there's a difference here. I'm asking about whether I can find electric field using Gauss law on the surface of the whole system. So electric field due to charge minus 8 coulomb and plus 3 coulomb using Gauss law. Can I do that? Again, your last guess was correct, so go ahead. Why not guess it? Nobody's gonna take your marks. Come on, just type any guess. Yes or no. Like Gauss law can be used to find the electric field on the surface or not. We are all learning. We are not prodigy. Okay. 3 people said yes. I'm talking about the electric field. And 3 people said yes. What about the others? Anybody for the no? Yeah, you feel like no. Okay, I'll drop the question. Meanwhile, people keep thinking. Yes, we can find electric flux, but not electric field. So answer to that question is no. We cannot find electric field because electric field at surface is non-uniform. So there are, if in your section 23.4 of the book, something like that, there are 4 rules given. There, let me answer. I'll address your questions. Okay. So there are 4 rules given for any Gaussian surface. For Gauss law to be applicable, Gaussian surface has to follow these 4 rules, at least one of them out of 4. So because of non-uniformity in the electric field here on the surface of the cube, you see the distance, there is a non-uniformity in the electric field. Okay, and there is no Gaussian surface. Yeah, I'm gonna repeat it again. Okay, let me finish and then you guys type the comment what you say. Okay, and definitely it is possible if there's none, if the other charge is not there, then definitely it's possible to find the Gauss law. We just applied it here, and then if this is equal to E dot ds. But we have to find the electric field due to another charge that is here. Okay, there is another charge that is outside the surface, outside the cube as well. This is non-uniform, and there are 4 laws that Gaussian surface has to follow. One of them, at least one of them, should follow. This is in your section 23.4. That there you can read them. Because of the non-uniformity in the electric field, Gauss law cannot be used, and what can be used is your Coulomb's law. You can use Ke by Q by R square, and then you consider Ri cap, then you consider this as vector, and then you sum the total electric field. E1. This is how you do it. Somebody asked me how to do it. This E1 is due to 3 nanocoulomb and E2 is due to plus 8 nanocoulomb. And this is how you do it for but Gauss law is not applicable, because if you do make any surface across these, they won't follow one of the laws. Okay, because there is a cube involved here. If these charges would have been in free space, then you can apply the Gauss law. You can consider a big fat sphere a gun. Does this address your questions? Any other question you can ask me, but I think it addresses your questions. I'm gonna move on when you guys say yes. Okay. Only move on then. Perfect. I assume yes for everybody else as well. If any doubt, you can still ask me, okay? Okay. Come on. Chapter 24. How are we doing on time? What's the time? Oh my god. Oh, we have half an hour. It's till 1:30 or whatever. Okay. I think I will be able to finish. How much we have left? Let me see. Not much. Let me try to do it. Okay. Chapter 24 talks about the electric potential. So electric potential between points A and B in an external electric field. The point is, to be precise, is electric potential is between the points, and in an external electric field is given as E dot ds, negative E dot ds, also U as QV. Potential energy is given as Q into V. Can any of you tell me why there is a negative sign in front of E dot ds? That's a question for you guys. Yes, Max. Christina, it is. If you change the signs, then there will be. If you change from B to A, then this will be positive. So I won't give that argument. And for Max, you said potential energy is negative of work performed on the system. We can, yes, but I'll give you the easier language, because potential energy would be negative. That means if there is a charge moving from A to B, it gains kinetic energy, then potential energy has to be negative, because total energy is always conserved. Did you guys get it? If K is increasing, then U should decrease. That's the easiest way to understand. That's how I always did. If U is decreasing, then K is increasing. Then total energy is conserved. That's because of energy conservation. Rephrasing it again. If your kinetic energy is negative, then your potential energy must be positive. Okay. Now, if your potential at infinity is 0, then potential due to a point charge is given as KEQ by R. That means, you remember this integral. If you say it's from infinity to point A, KEQ by R square. No, sorry. V to infinity, A to infinity, and KEQ by R square into dr. This is given as KEQ by R So you bringing the charge from, wait, I got a little confused there. You're bringing charge from infinity to point A. You always bring charge from the point of lower potential to the point of higher potential. So you assume that the charge at infinity, the potential at infinity is 0, and this is the equation. Then this is due to the point charge, you get this K/Q by R. That's how you got this. And if there is a group of point charges, then potential is given as, again, you put the summation before K/Qi bar I cap, and potential is a scalar, then you don't have to worry about the directions and stuff. And this should be E dot ds. You guys got this? How I did this proof, and why I did from infinity to A. You always bring from the point of 0 potential to the higher potential. That makes sense? Perfect. That's how you get this. Now, due to the continuous charge distribution, we get our favorite integral back. You all love to see it, right? So this is how you do it for the continuous charge distribution. You change q to dq and you put integral over all the charge. Now this is the questions I covered in the third DGD, that, or second DGD, like second DGD. Yeah. So first, 2 point charges. First question is 2 point charges are given, 5 nanocoulomb and -3 nanocoulomb, that they are separated by 35 centimeters. Doesn't matter the distance. What is the electric potential at point midway between the charges? So this is the direct application of the formula. You apply K/Q by R, and due to point charges, you apply the summation here. Okay. The apply potential due to discrete charges formula. What is the potential energy? You just type Q into V. That's it. That's your potential energy. Potential energy is negative. That means the system gains the kinetic energy, and the work is being done on the system. Okay. Question number 2, what I covered was this wire. Somebody bent it for us. They didn't like us, I guess. Then we had to find the uniform electric potential at point O, that is the origin here, and it is symmetrically placed around the origin, so that makes our life easier. So you have to use the integrals, and you divide the integral in 3 sections: -3r to -r, -r to +r, and r to 3r. I'll type it as, I'll give the coordinates. Makes sense to all of us, right? You can see the solution. I solved in second DGD. I think that was the last question of second DGD. Okay. Moving on to the fresh questions. Okay. This is again our familiar triangle. We solve, right? Now, 3 positive charges are located at the corner of an equilateral triangle. Again, that means angle subtended between 2 arms is 60 degrees. Find an expression for the electric field at the center of the triangle. We have to find the expression at the center of the triangle. 10. Right? That means this is 30 degrees. Right? How can I find this length? I know cos 30 degrees is given by base that is d by 2 by hypotenuse, that is d, that is, I'll give it as r. Okay, the distance between point Q to this. Okay, then I can find r as d by 2 by cos 30, or d by 2 cos 30 degrees. This is r, then this is r, this is r as well. Everybody agrees with me? If yes, say yes. Okay, perfect. Then this is cakewalk. Qi bar Ri. I don't have to consider about, there's no direction involved. This is a scalar quantity, I1 to I3. Then this will be Ke to Q by 2 cos 30 degrees plus Q by 2 cos 30 degrees, 2 cos 30 degrees. Everybody's with me? That's your answer to this question. Okay, I assume you guys agree. Then moving on to the next question. Again, our favorite rod is back. We love rods, right? So a rod of length L lies along the x-axis with its left end at the origin. It has a non-uniform charge density lambda. So point to be noted is it's non-uniform. This is V. This is the formula for V, potential, not the energy. We have to find the potential, not the energy. Okay. Glad you liked it. Where you got it. Okay. So the point to be noted, it is given as non-uniform. That means there's an alpha factor right there. Alpha is a positive constant. Okay. What are the units of alpha? I'm gonna ask you guys this. This is the last question for today before your midterm. So what is the units of alpha? Alpha is given as lambda by x. I'm gonna ask you guys this. What is the unit for lambda and what are the units for x? Then tell me the units for alpha. I mean it's a straightforward question. You just have to tell me the units of alpha. Lambda is charge per unit length. Coulomb per meter. Do you want to recheck it? I'm talking about alpha, not lambda. No. Okay. Coulomb per meter. 1 by meter. Coulomb per meter square. Everybody agrees? Perfect. Moving on to the real part of this question. Potential at point A. So we apply the simple formula of continuous charge distribution. Then V can be written as KE alpha dx by d plus x. This should be x as well. Everybody's with me in this. So I wrote q as lambda dx and lambda as alpha x dx. If you guys get it, do you want me to solve the integral? I think it's a straightforward integral. You want me to solve? You can use the substitution again. D plus x as u, then dx as du, then the limit goes from k substituting k alpha 0 to L u minus d by u du, that will be d, and y of y that will be L plus d. Oh, what happened? K alpha I think that's enough. Everybody can solve it from here. This will be log ln, and this will be just u, and just apply the limits. Should I solve it further? Say yes or say it's okay. Anybody has any problem? Okay. I'll write it. This is the answer. Okay, so I'm gonna conclude today's session now. I think there were time limit as well. Yeah, almost there. So what we covered today is we covered chapter 22, chapter 23, chapter 24, and there will be chapter 25 in your midterm as well, if that's what you guys told me in the Google Docs. And we covered 3 chapters, and the last chapter 25th was covered in TGD session 4, third. That was last Friday. That's why I didn't cover it here, and I didn't have time as well due to time constraint. And I hope you got the review. I hope it helped you guys. I wanted to brush up on all the concepts. I wanted you to revise before your midterm. And before concluding or ending the session, I want to tell you that before going to the midterm, you should revise what was covered in the class by your professor, all the questions, all the example he covered. Okay? And all the practice questions, but first should be the questions he covered, the concepts he covered in the class. You should revise on that. All the midterms are based on that. Okay?